Hello everyone, this is lecture 10 of course PE 645. In the previous lectures, we have covered multiple steps in the Radiomics workflow using artificial intelligence, including acquiring datasets, extracting Radiomics features such as first-order features and second-order features, including GLCM and GLRLM. Also, we highlighted the importance of normalization, and we developed the artificial intelligence model and got performance metrics and compared between multiple combinations to report the most promising machine learning model and scalar technique. We also presented the MinMax Plus, which is 18x standardized datasets for 2D and 3D, and we reported also that there are 2D datasets that can be accessed alongside 3D datasets, and you can manually download the datasets from the original website using the download link, or you can import it using the MinMax package in Python, and these datasets comes with the extension in BZ stored in an NumPy format. These are samples from the 2D images datasets, and these are for the 3D volumes. In today's lecture, we need to update our machine learning code to include further techniques such as feature selection, and we need to apply that on the 3D datasets named adrenal menace that reflects the adrenal gland. And this dataset is a 3D shape classification dataset that consists of shape masks from more than 1.5K left and right adrenal glands, which is reflecting 792 patients. And each element in the dataset has a shape of 28 by 28 by 28. This means that it contains 28 images, and each image has a shape of 28 by 28. Also, this dataset is split into 3 subsets: training, validation, and testing, with the following number of images. So this dataset is already split. So if we need a training subset, we can access directly the training subset, and if we need the testing subset, we can directly access the testing subset. So in this case, we will import the MinMax package and import the adrenal menace 3D from this package, and we'll let this package download the training subset and testing subset if we need, and we'll work on it directly without downloading anything else. So in this case, we will not read images and masks and apply ROI and so on from hard disk, but we will directly deal with the package and access the data on the fly. The second step, as we mentioned earlier, during dealing with the long dataset in project 2, we here are dealing with the 3D and highlighting the 2 approaches of the feature extraction again. So the first approach is to extract the whole features, including first order features, GLCM, and so on, and include all of them in your feature set alongside your class and apply the techniques on them. The second approach is to extract each feature set individually, such as extracting the first order features individually, the same for GLCM and so on, also for shape features, and you will apply your model and application or framework on each subset, and you can compare both approaches together. Without dealing with a specific type of features will get the high performance, or combining multiple features will get the high performance, and so on. Our aim is to get the most promising features that will report the highest performance. In project 2, we also emphasized what is the meaning of normalization and the importance of it. The same for machine learning models, and we mentioned that machine learning models are aiming to find patterns, aiming to discriminate between the different categories. So we have a set of techniques for normalization and a set of models for machine learning that can be utilized. Also, you can include whatever technique you need or whatever model for the machine learning in your code. These are only samples and examples that can be used. So first, we need to extract the features. Let's assume that we will deal with the second approach to extract the features individually, and we have learned how to combine all the features manually to get all features together instead of rerunning the code again. So go to script project 3, extracting multiple 3D features. In it, we imported the necessary libraries, including the MinMax, and from it we imported the MinMax 3D and also the helpers file. We have used the same dictionary that we used earlier with project 2, but here we included the shape features, and instead of using 4 or 8 connectivity types for GLCM, we here are dealing with 3D volumes, so we are subjected to 6 and 26 connectivity types, as we described during explaining the meaning of GLSZM and how to deal with 2D and 3D volumes. So we have a dictionary, and we can turn on and turn off the features. So simply, if this is true and others are false, this will be only executed. And also here we applied normalization and ignore zeros, and we removed the target size and included the split, and here we are declaring which split to use from the Radiomics, whether it's train, test, or validation. So simply we are setting here train. Again, we converted theta angles from degrees to radians. Then we checked which features are turned on. If none of them is turned on, then raise an error, because at least one should be turned on. We got the feature names as string to be included in the file name. Then instead of reading the files manually from the hard disk, we have here the MinMax 3D that we can get all of the images and apply feature extraction on them. So first, we created a function called MinMax dataset details. We passed the class, which is imported here, and this function is dynamic so that you can import any 3D or 2D dataset and pass only the class here and which split are you dealing with. And this function will return different information and details about this split for this class or this dataset. Inside this function that will be found in the helpers file, we are checking if no class is passed. We will import a default one, which can be the Radiomics 3D. If another class is passed here, then it will execute it and get the information and return it. Also, we created another function called MinMax loader iterator that will accept also the class name and the split, and it will return a data iterator. If you go to this data set, it will check also if a class is passed or not. If not none, it will load it. Otherwise, it will load the Radiomics 3D by default. Then it will access and print again the data information. Then it will get the different categories using the label from the information, and this function and the other one is only related to the MinMax. So these two functions are included in the category of custom functions for preprocessing special tasks. So let's continue. Here we are yielding each element, and yield here will yield a record one by one according to the calling or the iteration of this function. So there is a difference between return and yield. Return will return the element, yield will return as element and will wait for another iteration to get another element and return it. And this function will end after multiple calls equal to the number of elements in the dataset. Inside the iteration, we are extracting the volume, normalizing it and converting it into the range from 0 to 255, and we are using here the MinMax scaling. Then we convert it to unsigned integer 8, got the category and the corresponding name from the category dictionary, and returned the volume after normalization, the category name and the index. And here we are creating the iterator. The iterator will return one by one during the call here for the for loop. So inside this for loop, it will return a record. Inside this record, there are 3 elements, as we mentioned, the volume, category, and the index I, that we are going to use them in our feature extraction process. The total number of elements can be accessed using the number of samples from the dataset details that we got here, and we are providing the split we are using to get the corresponding number of elements because they differ from training, validation, and testing subsets. Inside this loop, we are creating the image features dictionary, and it's empty. And again, we are checking if the features are turned on or not. If it's turned on, it will be executed and extract features and then update that dictionary. And at the end of the code, it will append the image features that are extracted alongside the index and the category inside the history. And after executing all of the iterations inside this loop, it will convert it into a data frame and store it into a CSV file using the features path, which is defined here. And here we are storing it on this format. Here we are getting the class name, for example, the Adrian Minutes 3D. Then we are setting the concatenated features name and the split, train, test, or validation after capitalizing it, and the extension CSV for each of the features. To extract 3D features for first order features, we are looping on each image inside the volume individually and storing them into a list, then converted the list into a data frame and got the average across all slices, and that average is converted to a dictionary that is appended to the image features. So the idea is simple. First order features are extracted on each slice, combined all of them into a data frame, got the average for each feature, got that average and appended the mean features into the image features dictionary. For 3D GLCM, we got a function to calculate the 3D GLCM or co-matrix, and based on it, we got the GLCM features. The same for GLRM, we got a function for GLRM 3D, the same for GLSZM matrix, and for shape features, we have a function also for shape features 3D. So all of the features, we got functions for the corresponding 3D calculations, but for the first order features, we are overcoming that challenge by slicing, by getting the features across each slice and getting the final average and using that average for the whole volume. When you execute the code, it will first print the details in front of you for the selected dataset, which is Adrenal Minutes 3D, and then we'll start to loop on the elements of the training subset as we defined in the code and extract the different features, and by the end it will store these features in a CSV file. As you see here, there is the class Adrenal Minutes 3D, the description of the dataset and URL, and the type of the task, binary classification, the labels, 0 for normal, 1 for hyperplasia, the number of samples for training, validation, and testing, and it started to loop on the different elements for the training subset, which is around 1000 instances, and it will complete the execution and then store the data into a CSV file. For the second part of the project 3, Machine Learning Classification Revisited, this code is similar to code 24, Project 2, Machine Learning Classification, but here we are dealing with a 3D stored dataset. So we are again defining the base directory, the dataset file name, and the storage folder name that the code will store the confusion matrix and pickle files into it. Then we create the directory, define the set of scalars and models, and you can add different models as you wish, but don't forget to update the function in the helpers file to create an object from the defined algorithm if it doesn't exist there. Then here we created the history list, looped on the models and the scalars. Then we created try catch or try except block that will handle that code. If there is an error, it will not raise an error, but it will print it into the command window and continue the execution. Here we executed the machine learning classification version 1 and got the corresponding output, metrics, plot object, and objects that will be stored in a file. Then we saved the figure and saved the pickle file, the object inside the pickle file. Then we appended the model scalar and matrix, and at the end we stored all of that into the history data frame and stored then into a CSV file using that path. As you notice here, we can execute this one. After completion, we can comment this and uncomment this for executing the GLCM, and the same for others. And we also can execute for all of the features. So when you do that, for the first order features, you will get the corresponding output, or you can get similar ranges for the first order features. It's not mandatory, as we mentioned, to get exact metrics, but it can be close to these metrics above or below. Here we are reporting the weighted matrix because the number of samples per category are not equal. So it's better to report the weighted matrix as we illustrated earlier in a previous lecture. We sorted the matrix, which is the weighted average, in a descending order. And this means the first one is the top or the highest performance. As you notice, we got a high recall, but a very low specificity. And if you notice here, a high recall means a high value according to the positive class. And you may wonder which is a positive class in our confusion matrix here. In our confusion matrix, you will notice that this would be index 0 and this would be index 1 according to the label encoding or the automatic label encoding, which is provided in our code. So the recall will be related to the normal. That's why we are getting a high value, because here we have 180. And specificity reflects the negative class, which is hyperplasia. Medically, this should be reversed or swapped, but by all means, we know in our case here and example, the recall is reflecting the normal and specificity is reflecting the hyperplasia, whether it's correct or not, swapped or not. But according to the metrics in hand, the best model reported high recall and low specificity, and we may not accept that model because of the low specificity, whether it's normal or hyperplasia or whatever class we are targeting. And this is the result of the first order features. When we execute the GLCM features, we get a better specificity and a weighted average of 80. But in the first order, we got a weighted average of 73. So in this case, we can say that GLCM is better than the first order features. When we do the same with the GLRM features, we get similar specificity but lower recall and the lower weighted average. So in this case, we can say that GLCM is still better than both first order and GLRM features. And for GLSZM, the same case. Comatrix features are better than this one also. But for shape features, as you see here, we got better specificity and better recall and better weighted average. So here, shape features is better than others according to the weighted average or specificity or recall. And when we combine all features together and get the performance, we get a better performance, as you see, better specificity and better weighted average. But in all cases, the specificity is still low. But just as a comparison, we can say that combining all features in this case is better than dealing with the individual subsets separately. So the idea here is we are dealing with each subset individually and then combining all features together and check whether the performance is increased or not. It's not mandatory to get high performance by combining all features. You may apply that on a different example and get poor performance if you combine all features together. But if you use individual subsets, let's say GLCM or shape features, you may get better performance. So until this moment, we are dealing with all of the features together. But we can say that not all of the features are relevant to the category or the problem. This means that we have a set of features, but not all of them are helping the model to train well and find a way to discriminate between the categories. So we need a technique to select the most promising features first and then use that feature set or subset and apply that after filtration to the model. And here comes a preprocessing step is called feature selection. And feature selection is a critical process in machine learning that involves identifying and selecting the most promising relevant features from a dataset. And this will help improve the performance of machine learning models that can reduce overfitting, decrease training time, and enhance model accuracy. There are many techniques for feature selection, including filter methods, rubber methods, and embedded methods. And it worth noting that you may apply feature selection with a specific ratio and still get poor performance or lower performance than combining all of the features. So it's worth noting here that feature selection is a tool that can help, but it's not mandatory to improve the performance. And this means that you need to select the best ratio or the number of features to be selected to increase your performance. In other words, let's say we are testing our model to 100% of the features, 90% of the features, and 70%, for example. Then we need to apply all of these combinations to our model and check which is the best. Theoretically, selecting the most promising features will increase the performance. Maybe the performance will increase here or here, but sometimes getting all of the features together can perform better than getting a subset, and it depends mainly on the problem and the algorithm you are using. By all means, utilizing feature selection can help improve the performance. So the first type of the feature selection techniques or categories is filter methods. And filter methods use statistical techniques to evaluate the relevance of features, and they are independent of any machine learning algorithm and can include techniques such as correlation, chi-square, mutual information, and ANOVA F-value. And the situation here is simple. We have set of features, let's say column A, column P, and column C, and the category, let's say Y. Here, the filter methods, let's say you are using the chi-square test, measures the chi-square relevance between each feature and the category and get a score here, and the same for B and the same for other features. And then according to that score, it sorts them and pick the highest score or lowest score according to the technique. Assume that the higher the score, the better the feature column. Then if we have 3 features and we need to pick only 2 or 1, then the top 2 or top 1 will be picked from that method. The chi-square test measures the independence between categorical variables. In the context of feature selection, it evaluates if the feature and the target variable are independent. Mutual information measures the amount of information obtained about one variable through another variable. In our context here, it quantifies the dependency between the feature and the target variable. And the ANOVA value measures the ratio of variance between the groups to the variance within the groups. It's used to determine if there are any statistically significant differences between the means of different groups. By using these techniques or other statistical techniques, the aim here is to get a score for each feature vector, sort them, and pick the number of features which are required by your framework. Rubber methods evaluate the usefulness of features by training a model. So here we are dependent on a specific machine learning model on different subsets of features. The common rubber methods include forward selection, backward elimination, and recursive feature elimination. For forward selection, we are starting by an empty set and iteratively add the most significant feature at each step. Let's say we got 3 steps, so we are getting the most promising of them, adding it into our feature set, then evaluate the model performance after each addition. So we will get here a score. Then we will add also a second one and get another score, and the same for other steps. And we are going to do that until a stopping criteria. And here the stopping criteria is when adding new features will no longer improve the performance. For backward elimination, we will begin by all of the features inside our subset, and we will do the opposite. We will iteratively remove the least significant feature at each step. So assume we are beginning with 5 features. The next step should be 4 features, and the same until we reach a stopping criteria. And again, the stopping criteria is when removing any feature worsens the model's performance. For recursive feature elimination, we will use a model's feature importance or coefficient to rank the features, and recursively prunes the least important features in rounds. Then we will train the model on the reduced feature set at each iteration, and this will continue until the desired number of features is reached. For the last one, embedded methods, we are performing feature selection during the model training process, such as using the lasso or L1 regularization and decision tree based methods. To understand it better, let's check this figure. We have a feature set here, and we need to select the most promising features or the top N features. For filter methods, we are selecting the subset first, and then we will apply it later to the learning algorithm that we need and get the performance. And selecting the subset here is done individually away from the learning algorithm or the machine learning model using a statistical method. For the wrapper technique, here we are dealing with selecting the feature and the learning algorithm iteratively, whether you're using forward selection or backward elimination or whatever approach you are dealing with. Simply, we are getting a subset, applying it to the machine learning model, then iteratively get the performance back to the model, then adding or removing according to the technique, then rerun again the algorithm and check the performance, and it will do that behavior until it reaches a suitable stopping criteria. After that, it will train the final model and get the performance. And for the embedded approach, here we are dealing with feature selection during the training by decreasing the importance of some features or increasing the importance of some features. Let's say, for example, that we have 3 features, X, Y, and Z, that will lead to the performance P. So simply combining them will lead to a specific performance. What about if we added here half of the importance of Z? It can lead to other performance value. The same for Y, the same for X. So during the training process, the weights of each feature, it changes, and this weight will reflect the importance of the feature. By ending the training process using the embedded approach, we can use these weights or these coefficients and the corresponding performance that should be the highest performance according to these coefficients. By using any technique of those, we need to reach to the most promising feature subset. So here we improved our code to include the feature selection techniques. So go to project 3 machine learning classification version 2, code number 37. Here we are defining the training and testing folders. So during the feature extraction, we extracted the features for both training and testing subsets. And I will highlight after a while the importance of doing that and what it changes inside the code to load the testing subset. So here we created the folder, defined the scalars list, models list, similar to the previous code, but here we defined feature selection techniques and feature selection ratios. And you can include whatever ratio you need as a percentage and whatever technique you need. And I will tell you how to add other techniques into this list and the corresponding function. So here we created 4 loops. And for now, let's say we will deal with 4 inner loops, and I will raise what is the disadvantages of using that approach. So for these 4 loops, one for models, one for the scalars, one for feature selection techniques, and the last one for feature selection ratios. We created a new function called machine learning classification version 2 that accepts similar arguments to version 1, but here we included feature selection technique and feature selection ratio. We also included the test file path, and this is the first change to accept the test file as a path instead of a ratio. The rest of the code is similar to the previous one, but here instead of only storing model and scalar, we are storing the 4 values: model name, scalar name, feature selection technique, and feature selection ratio. And last, we are exporting them and saving them to a CSV file into the target directory. So now let's focus on this function, machine learning classification version 2. This function in the helpers file begins by reading the data from the dataset file path, drop the first column if it's required or this flag is true. Then here we are using drop now for columns and rows, and we are using any here to drop if any value is null, here for columns and here for rows. Then we created the features X here and got the names that will be used later for feature selection. Then we got the target, which will be according to the target column. Then we encoded Y according to the created global encoder, and we got here the Y encoded values. If the test file path is provided, and in our case here it's given, we are going to read the data, drop the first column as we did with X and Y. Then we use the current columns stored here in that variable to get X test and got the Y test using target column and encoded using the created fit label encoder here. Then this block means that we are splitting between training and testing subsets, and here comes the importance of getting train test subsets individually. This will avoid any concern about the data leakage, especially if we are dealing with patients or cases and each case or patient got multiple images. So the train test subsets are provided by the authors of the Adrian Menes 3D dataset. So we are providing both of them. So here it checks if the test file path is provided, then we will deal with the given file. Otherwise, if no test path is provided, then we will use the traditional way by splitting the given file into train test subsets according to the test ratio. Next, we handled the scalar name. We checked first if it's not none. If so we defined the scalar, applied fitting and transformed the training and testing subsets and converted them to data frame so they can be used correctly with the perform feature selection method. If the scalar name is none, then this block will not be executed and none value will be assigned to the scalar variable. Then we checked also if the feature selection is not none, we applied feature selection, otherwise the feature selection variable will be none. Both of them will be helpful during the storage of the objects. So let's return to perform feature selection. It accepts the name, the ratio, the training and testing subset. Inside it, you will find multiple techniques, but first we got the number of features from the ratio by multiplying the number of features from the training subset to that ratio and dividing that percentage by 100 and converting them to an integer to get the number of features. Then we applied bounding to the number of features to be at least 1 and at most the number of features in the subset. Then we made a small check to check if the number of features is higher than the exit train. It will raise an error, but by all means this will be bounded in this case. Also, if the number of features is equal to the number of features in the training subset, then we don't need to apply feature selection and we will return the original train and test subset. Then we made a set of if-else-if conditions. For each block, a specific technique is handled. For example, principal component analysis, random forest, recursive feature elimination, chi-square method, mutual information, ANOVA F-value, linear discriminant analysis, and also you can add any technique for feature selection in another else-if block so that you can use it later here in your feature selection techniques. At the end, checks if we need to return the features alongside the train and test subsets and the object. If so, return the feature as a fourth element. When the function is executed, we will get the three objects, the train and test subsets after feature selection and the feature selection object. Then we did similar to version 1, created the model, applied fitting, prediction, created the confusion matrix, calculated the performance metrics, created the figure, and finally returned the matrix, plot object, and objects. And after executing the function inside the loop, the three objects will be turned and the rest of the iteration will continue until it completes the four loops and will end by storing the data into the history file as a CSV file. It worth noting that creating multiple inner loops will increase the time, and this is one of the disadvantages of using multiple loops, and this is called grid search by looping on all of the combinations for all of the lists. And the disadvantage of applying grid search here is by increasing the number of elements in each list will increase the time complexity for the execution. For example, assume each list contains 10 elements, then by executing 4 inner loops to get all of the combinations, then this will be 10 raised to the power of 4 number of iterations, and this will take long time. And we will cover how to handle that in the next lecture by using hyperparameter optimization techniques from the Optina framework, so it's worth to highlight that point. After executing the code for the first order features, we got the following performance, and there is a change in the performance due to first the feature selection, and second we are differentiating between the training testing subset. Here we applied train test split, but here we used an external test subset and also we applied feature selection. From that, the weighted average decreased, but on the other hand the weighted specificity increased. And for GLCM features, also the weighted average decreased, but the weighted specificity increased. And here for this experiment, we didn't use any feature selection because this was none. Again, the change here happened because of using an external test subset. But by all means, the weighted average as a whole performance or an average performance decreased from 80 to 77. Using GLRLM features, the performance increased to 83, and by using GLSZM features, the performance increased to 78 and the specificity increased to 71 using random forest with 80% as a feature selection ratio. Using shape features increased also the performance and the weighted specificity slightly, and combining all of the features together increase the weighted specificity and the weighted average using recursive feature elimination with 90% as a feature selection ratio. And this is a comparison between with feature selection and without feature selection for all feature types here and here. And from that, we can say that applying feature selection to this dataset increase the performance, including specificity and precision. And this happened using stochastic gradient descent as a machine learning model, max absolute technique as a scalar technique, recursive feature elimination as a feature selection technique with 90% as a ratio. So in this lecture, we recapped what is the meaning of Radiomics workflow. Then we went to the MinMax version 2 dataset and cover that it contains 2D and 3D data that can be used whether you are downloading them manually or using the package MinMax 3D, MinMax in Python. Then we extracted the different features, including shape, GLCM, and first order features, applied that on the MinMax 3D dataset. We extracted for both training and testing subsets. Then we revisited the machine learning classification code and executed it on the new extracted features. Then we updated our code to include feature selection and also to include an external testing subset. Finally, we compared between including feature selection and excluding feature selection, and we highlighted that in our experiment using the MinMax 3D, that including feature selection enhanced the performance as presented in the weighted average and weighted specificity.